Download this code from codegive.com, link in the description below. Understanding and debugging llvm loop unroll miscompile issue 51102. This tutorial dives deep into llvm loop unroll miscompile issue 51102, providing a comprehensive understanding of the bug, its impact, and methods for debugging and potentially contributing to a fix. We'll cover 1. Introduction to loop unrolling and its benefits. 2. Overview of llvm and the optimizer. 3. Detailed breakdown of issue 51102. 4. Reproducing the bug, a code example. 5. Analyzing the IR, intermediate representation, code. 6. Debugging techniques using llvm tools. 7. Understanding the root cause, as known/speculated. 8. Potential fixes and mitigation strategies. 9. Contributing to llvm, a general guide. 10. Conclusion. 1. Introduction to loop unrolling and its benefits. Loop unrolling is a compiler optimization technique that aims to improve performance by replicating the body of a loop multiple times within the code. The main benefits are: reduced loop overhead, fewer loop iterations mean fewer branch instructions, condition checks, and loop counter updates. This overhead can be significant, especially for small loop bodies. Improved instruction level parallelism, ILP unrolling provides more opportunities for the processor to execute instructions from different iterations in parallel, exploiting instruction level parallelism. Improved cache locality by executing more instructions in a single block of code, unrolling can improve cache locality, reducing memory access latencies. Enabling other optimizations. Unrolling can sometimes expose new optimization opportunities that wouldn't be possible with the original loop structure. For example, consider the following simple loop. After unrolling this loop 2 times, it would become. While this looks less elegant in a small example, the elimination of loop control overhead and the potential for the compiler to schedule instructions for better parallelism often makes up for the increased code size, particularly in performance-critical sections. 2. Overview of llvm and the optimizer. llvm, low-level virtual machine, is a modular and reusable compiler infrastructure project. It's used in a wide range of applications, including language compilers, static analysis tools, and just-in-time (JIT) compilation. A crucial part of llvm is its optimizer, which transforms the intermediate representation (IR) of the code to improve its performance. The optimizer consists of a series of passes that perform specific optimizations, such as dead code elimination, removing unused code, constant propagation, replacing variables with their constant values, instruction combining, replacing multiple instructions with a single, equivalent instruction, loop unrolling, unrolling loops, as discussed earlier. Vectorization, using SIMD instructions to perform operations on multiple data elements simultaneously. Inlining, replacing function calls with the function's body directly. The optimizer passes are applied in a specific order to achieve the best possible performance. A miscompile occurs when one or more of these passes introduce an error that causes the generated code to produce incorrect results. 3. Detailed breakdown of issue 51102. Issue 51102 on the llvm GitHub repository, and its related duplicates/predecessors, usually refers to a specific miscompile related to loop unrolling. The details can vary depending on the exact issue number and the llvm version involved, but the core problem typically stems from the loop unroller making incorrect assumptions about the loop's behavior or interaction with other optimizations, resulting in incorrect code generation. Here's a common scenario that often triggers such miscompiles. Aliasing issues. The loop body might involve pointers that alias, meaning they point to the same memory location. The loop unroller might not correctly account for these aliasing relationships, leading to incorrect data dependencies and incorrect code. Predicate registers. Some architectures, example Itanium, ARM save, use predicate registers to conditionally execute instructions. If the loop unroller doesn't handle predicate registers correctly, the unrolled code might execute instructions in the wrong order or under the wrong conditions. Induction variable updates. Incorrectly updating induction variables during unrolling can lead to errors. Induction variables are variables that are incremented or decremented in each loop iteration, example the loop counter I in a for loop. Interaction with other optimizations. The miscompile can sometimes arise from an unexpected interaction between loop unrolling and other optimizations, such as vectorization or instruction scheduling. Key characteristics of loop unroll miscompiles. Data corruption. The most common symptom is data corruption. The program produces incorrect results due to incorrect memory writes or reads. Specific hardware/compiler flags. The issue might only manifest on specific hardware architectures, example ARM, PowerPC, or with certain compiler flags, example O3, FastMath. Small, targeted code changes. Often, a small change to the source code can trigger or eliminate the miscompile, which makes it difficult to track down. Intermittent/random behavior. Sometimes, the miscompile might appear to occur randomly, making debugging even more challenging. This can be due to slight variations in memory layout or instruction scheduling. 4. Reproducing the bug, a code example. The most crucial step in addressing a compiler bug is to have a reliable reproducer, a small, self-contained code snippet that consistently triggers the miscompile. Finding a minimal reproducer can be incredibly difficult but significantly speeds up the debugging process. The actual code that triggered issue 51102 might be highly complex, but let's craft a simplified example that demonstrates a potential aliasing issue that can be exposed by loop unrolling. Important *, this example might not exactly reproduce the reported bug, but it captures a common scenario where loop unrolling can cause miscompiles. Explanation of the example *. 1 corrupt _data function *. This function takes an integer array data and its length len as input. 2 initialization loop *. The first loop initializes the array elements with their index values, data 0 equals 0, data 1 equals 1, etc. 3 corruption loop *. The second loop is designed to modify the array elements in a way that exposes potential aliasing problems. It assigns data I the value of data I plus 1 plus 1. This loop creates a data dependency. The value of data I depends on the value of data I plus 1. 4 main function *. The main function creates an array data, calls corrupt _data to modify it, and then prints the contents of the array. Compiling and running with and without optimization *. Compile with optimization, likely to expose the bug if it exists in the loop unroller. Compile without optimization, should produce correct results. Expected output, without optimization. If the O3 version produces a different output, especially if it seems completely nonsensical or contains unexpected values, it could indicate a miscompile due to loop unrolling or related optimizations. The exact incorrect output can vary depending on the compiler version, architecture, and other factors. 5. Analyzing the IR, intermediate representation, code. The llvm IR is a low-level, platform-independent representation of the program's code. Analyzing the IR code can help you understand how the optimizer is transforming the code and where the miscompile might be occurring. Generating the IR asterisk. You can generate the IR code for the example program using the emit llvm flag. This will create a file named corrupt.ll containing the IR code. Reading the IR asterisk. The IR code can be quite complex, but here are some key things to look for. Asterisk loop structure asterisk examine the for loop in the corrupt_data function. Look for the loop.header, loop.body, and loop.exit basic blocks. Asterisk induction variable updates asterisk identify the instructions that update the loop counter I. Asterisk memory access instructions asterisk look for the load and store instructions that access the data array. Pay special attention to how the array indices are calculated. Asterisk metadata asterisk llvm-ir contains metadata that provides additional information about the code, such as loop unroll hints and aliasing information. Look for metadata like llvm.loop. Example IR snippet, potentially problematic. In this snippet, the instructions calculate the addresses of data I and data I plus 1, %arrayx and %arrayx.next. If loop unrolling incorrectly reorders or duplicates these calculations without considering the potential for data I and data I plus 1 to overlap, alias, it could lead to a miscompile. The optimizer might assume that writing to data I doesn't affect the value of data I plus 1, which is incorrect in this case. 6. Debugging techniques using llvm tools. llvm provides a number of tools that can help you debug miscompiles. Opt the opt tool is the llvm optimizer. You can use it to run individual optimization passes or a sequence of passes on the IR code. This can help you isolate the pass that is causing the miscompile. To run a specific pass, this command runs only the loop unroll pass. You can then examine corrupt_unrolled.ll to see the result of the unrolling and check if it introduces any errors. You can use debug pass equals structure to see the order and names of the executed passes. The lie tool is the llvm interpreter. You can use it to execute the IR code directly, which can be helpful for verifying whether the IR code is correct. Compare the output of lie with the expected output. File check is a tool that allows you to verify that the IR code matches a specific pattern. This can be useful for testing the correctness of optimization passes. You can create a .test file with expected output and then use file check to verify that the generated IR matches the expectations. Print after all / print before all * these llvm flags are invaluable. They print the IR after / before every single optimization pass. This lets you narrow down exactly which pass introduced the miscompile by comparing the IR before and after the execution of that pass. Be warned, this will produce a lot of output. Example debugging workflow * 1. Reproduce the bug * confirm that the 03 version of the code produces incorrect results. 2. Generate IR * generate the IR code using clang 03 emit llvm corrupt.co corrupt.ll. 3. Isolate the pass * use opt with print after all and print before all, and maybe debug pass equals structure, to identify the specific optimization pass that is causing the miscompile. This is the most tedious but most important step. 4. Analyze the pass * once you've identified the culprit pass, carefully examine its implementation in the llvm source code, usually in lib/transforms. Understand the logic of the pass and how it transforms the IR. Look for potential errors in the pass's reasoning about aliasing, data dependencies, or instruction ordering. 5. Create a minimal test case *. Try to create an even smaller, more focused test case that reproduces the miscompile. This will make it easier to understand and fix the bug. 7. Understanding the root cause, as known/speculated. The exact root cause of issue 51102, or similar loop unroll miscompiles, can vary widely depending on the specific code and llvm version. However, here are some common root causes that are often involved. Incorrect alias analysis. The alias analysis component of llvm's optimizer is responsible for determining whether two memory accesses might refer to the same memory location. If the alias analysis is incorrect, the optimizer might make unsafe transformations that lead to data corruption. Loop unrolling can exacerbate aliasing problems because it increases the number of memory accesses and makes it more difficult to track dependencies. Missing data dependencies. The optimizer might incorrectly assume that two instructions are independent when they are actually dependent on each other. This can happen if the optimizer doesn't correctly account for aliasing or if it makes incorrect assumptions about the order in which instructions are executed. Predicate register handling errors. On architectures that use predicate registers, the loop unroller might not correctly handle the predicates, causing instructions to be executed under the wrong conditions. Integer overflow/underflow assumptions. The unroller, or other passes, might make assumptions about the ranges of integer values used as loop counters or array indices. If these assumptions are violated, example due to overflow, the code can misbehave. Suboptimal register allocation. Loop unrolling increases register pressure, which can lead to suboptimal register allocation. If the register allocator spills values to memory too frequently, it can degrade performance and even introduce errors. 8. Potential fixes and mitigation strategies. Fixing a loop unroll miscompile typically involves one or more of the following. Improving alias analysis. Enhancements to llvm's alias analysis infrastructure to more accurately track aliasing relationships. This is a complex task, as alias analysis must be both accurate and efficient. Adding data dependency checks. Introducing more robust checks to ensure that the optimizer correctly accounts for data dependencies before making transformations. Correcting predicate register handling. Fixes in the loop unroller, or other relevant passes, to ensure that predicate registers are handled correctly on architectures that use them. Adding range checks. Incorporating range checks to verify that integer values are within the expected bounds. Improving register allocation. Enhancements to the register allocator to reduce register spills and improve performance. Disabling loop unrolling. In some cases, the easiest way to mitigate a loop unroll miscompile is to simply disable loop unrolling for the affected code. This can be done using compiler flags, example no unroll loops, or by adding a llvm.loop metadata tag to the loop in the IR. Rewriting the code. Sometimes, the miscompile can be avoided by rewriting the code in a different way that avoids the problematic aliasing or data dependencies. This is not ideal, but it can be a useful workaround. Example mitigation, disabling loop unrolling. You can prevent loop unrolling for a specific loop by adding the llvm.loop metadata. To do this, you'll need to modify the IR code. Add the following to the end of the loop's header block in the IR. This metadata tells llvm's optimizer not to unroll this specific loop. You can achieve a similar effect by adding pragma-clang loop unroll, disable, before the loop in your C code, which will instruct the compiler to generate the appropriate metadata. 9. Contributing to llvm, a general guide. Contributing to llvm is a rewarding but challenging process. Here are the general steps. 1. Set up your llvm development environment ***. Download the llvm source code from the GitHub repository, https://github.com/llvm/llvm project. ***. Follow the instructions in the llvm documentation to build llvm. ***. Configure your development environment, example set up code editors, debuggers. 2. Find a bug to fix, or a feature to implement. ***. Browse the llvm bug tracker, Bugzilla, for open issues, https://bugs.llvm.org/. Look for issues that are marked as good first bug or beginner friendly. ***. Discuss your plans with the llvm community on the llvm mailing lists, llvm dev. 3. Develop a fix, or implement the feature. ***. Create a local branch in your Git repository. ***. Write the code to fix the bug or implement the feature. ***. Write unit tests to ensure that the fix is correct and doesn't introduce new problems. This is absolutely crucial. ***. Follow the llvm coding style guidelines, https://llvm.org/docs/codingstandards.html. 4. Test your changes ***. Run the llvm test suite to ensure that your changes don't break existing functionality. ***. Use lit, llvm integrated tester, to run the tests. 5. Submit your changes for review ***. Create a patch file using git format patch. ***. Submit the patch to the llvm code review system, Fabricator. ***. Address any feedback from the reviewers and revise your patch as needed. 6. Commit your changes ***. Once your patch has been approved by the reviewers, it can be committed to the llvm repository. Important tips for contributing ***. Join the llvm community ***. Subscribe to the llvm mailing lists, participate in discussions, and attend llvm conferences. Read the documentation ***. The llvm documentation is a valuable resource for understanding the llvm architecture and coding standards. Start small. Don't try to tackle large, complex problems right away. Start with smaller, more manageable tasks to get familiar with the llvm code base. Ask for help. Don't be afraid to ask for help from the llvm community. The llvm developers are generally very helpful and willing to provide guidance. 10. Conclusion. Debugging loop unroll miscompiles, like the one potentially causing issue 51102, can be a challenging but rewarding task. It requires a deep understanding of llvm's optimization passes, alias analysis, and code generation process. By following the debugging techniques outlined in this tutorial and engaging with the llvm community, you can contribute to making llvm a more reliable and efficient compiler infrastructure. Remember that finding a minimal reproducer, carefully analyzing the IR code, and using llvm's debugging tools are crucial steps in the debugging process. Furthermore, understanding the potential root causes of loop unroll miscompiles, such as incorrect alias analysis or missing data dependencies, can help you narrow down the source of the problem. Good luck, and happy debugging.